Okay, in this video, it's a continuation of section 9.6. And all we want to do is work out a problem 9.3, utilizing some of these equations that we have derived. So let me write those down and get ahead of it so that you don't have to wait for that, and we'll work through that problem. Okay, so here's the conditions for this problem. It says I have a not quite ideal transformer. I'm not exactly sure what that is, but you know, we have ideal and practical. I'm not sure what a not quite ideal transformer is. I do, I'm just kidding. But anyway, we're sort of borrowing some from both worlds here. But anyway, not really important to work in this problem. The not quite ideal transformer has 90 turns on the primary side, okay? And it has 2,250 turns on the secondary side. It's connected to a 120 volt source at 60 hertz frequency and has a magnetizing current of 4 amps. He says, what is the effective voltage across the secondary terminals? Okay, well, you know, if this were this side, you know, we have equations that work for this, but we've never really had to deal with something like this, because here's the secondary side over here and there's nothing connected to it. There's no source. I mean, well, I don't know how does that work. So what I'm going to do is I'm going to utilize my turns ratio to determine what that voltage would be. And it gets back to equation 9.5 that says this relationship is equal to this relationship. Okay, proportion, right? And so I know N1 is 90. I know N2 is 2,250. And I know that E1 is, what is E1? I know that, well, I don't need that, do I? Because if I have either one of these, I have the turns ratio. So anyway, so I can calculate the turns ratio, and that is going to be 90 over 2,250. So let me pull the calculator out here. Okay, I went ahead and added something here. I think it's important because, you know, in the first section of this, he looks, you know, at this turns ratio and isolates that, and he reasons this thing out that since this side has 90 turns and this has 2,250 turns, this is, if you multiply, you know, if you divide that into that, it comes out to be 25. So, you know, he's saying that at this stage, we should be able to reason that this voltage on the secondary side would be 25 times greater than that on the primary side. Well, I'm not sure we're there yet with this. So what I thought is probably better is let's look at this and use our equation 9.5, and let's put in everything that we know. We know that N1 is 90 and N2 is 2,250, and that E1, you know, this was 120 volts, and so this is going to be 120 volts induced. And so, you know, basically what we're doing is we're solving for E2, or the secondary voltage. And when we do that, if you multiply 120 by 2,250 divided by 90, you get that E2 is 3,000. I don't know what's going on with this iPad here. It's very squirrely today. It comes out to be 3,000 volts. Okay. Well, what we can see from that is, you know, if we can understand that, you know, on the primary side, this was 90 turns, and that on the secondary side, it was 2,250 turns. And that relationship is that this secondary side is 25 times greater than the primary side. It also goes to reason that the voltage will reflect that same relationship. So what I'm saying is, if I have more turns on the secondary than I do the primary, whatever that number is, the voltage will also reflect that. So I could have just determined the voltage ratio and then made the determination that the secondary voltage would be 25 times larger. And in this case, 120. And of course, that comes out to equal 3,000 volts. Now, another thing, I don't want this to pass you by, is, think about that just for a second here. How incredible that is that we could take 120 volts into this device and we could get 3,000 volts out of it. And what he does in the second part of part A is, he goes through that calculation where we're just plugging into equation 9.5 and looking at those relationships. Okay, so two things there, and here in a little bit, once you get used to this, you'll just look at this and you'll see these things. But I thought maybe initially it might be important for us to actually go through that using this equation 9.5. Okay, now let's look at the second part of this. In part B, ask us very simply, what is the peak voltage across the secondary terminals? Well, initially he was asking for effective voltages. So this is an RMS voltage of 3,000 volts. So 3,000 volts. And then I want to know the peak value. So I'm just going to multiply that by the square root of 2, right? And what I would get is square root of 2 times 3,000, or 4242 volts would be the peak voltage. Again, all this is sinusoidal. And so we're looking at a peak voltage for this 3,000 volt RMS of 4242. Okay, so that's that part. And then the third part is asking the question, the instantaneous voltage across the secondary when the instantaneous voltage across the primary is 37. Okay, so again, remember all of this is sinusoidal, and he's asking us for an instantaneous value. And we may have I just lost something here. Looks like a stop here with my application. Hold on, let's see if I can get back. Okay, hopefully I'm back and can finish this. But if we were given this problem, say in a circuit analysis class, we might go through a major calculation to get there. But really in part C, all we got to remember is that anytime, whatever voltage we have on the primary side, the secondary side will be 25 times more than that because of our turns ratio that we calculated earlier. Okay, so that's a really makes a lot of these problems so much easier to work with. So if I'm looking at a point in a sinusoidal waveform where I'm at 37 volts and I want to know what would be reflected out here, really all I got to do is say 37 times 25, and 37 times 25 gives me 925 volts. So if I had 37 here, at that particular instance, I would have 925 volts here. Again, these are not just theoretical, out of the sky values. These are real numbers. These are the real kind of things that you see in a transformer. You see that level of voltage transformation or increase. Okay, so that's 9.6.